Hello everyone, today my presentation is going to be about our study on the recent microseismic activity around Digana in Sri Lanka based on modeling seismic data. There are two objectives to my presentation today. First is to demonstrate a set of tools that can be used to analyze seismicity with a sparse network of seismographs as in Sri Lanka, and the second is to present the most up-to-date results from seismic modeling of the microseismicity in Digana. Well, Sri Lanka is generally considered to be seismically safe. However, speculative historical records say that there was a magnitude 6 earthquake close to Colombo, and Fernando and Kulasinger from a short-term seismograph network deployment in the 1980s, shown by the purple triangles in the map on the right-hand side, provide evidence to say that 2 to 3 micro earthquakes occur in the country every month, and of these micro earthquakes, about 2 to 3 are strong enough to be felt by people annually. So, how can earthquakes occur in Sri Lanka even though it is far from a tectonic plate boundary? Well, earthquakes can occur in both the interplate and intraplate tectonic settings. As you can see in the figure on the bottom left, Sri Lanka is located in the Indo-Australian plate, and the collision of this plate with the Eurasian plate produces an intense, compressive plate-wide stress field. Around Sri Lanka, the maximum compressive stress reach values greater than 40 megapascals with an orientation in the north-northwest direction, as shown by the figure on the bottom right. And the crust in Sri Lanka is called old and therefore cold, and this resists deformation. Nonetheless, the high stress conditions prime favorably oriented faults to fail, and therefore we can expect the occasional release of pent-up tectonic stresses by slip along these faults. And the sense of slip of these faults can be thrust, strike slip, or oblique slip. And during the last 6 months, there were many records of seismicity within the island. And from these, the most critical and significant were the earthquakes that occurred around Haragama and Anuragama in Digana, as they occurred in the vicinity of the Victoria Reservoir and the dam. And 5 earthquakes occurred between August and December 2020, and they were felt by people living around these areas. The figure on the left shows the intensity of the earthquake that occurred on the 29th of August 2020, and it indicates the highest intensities were felt around Haragama, Anuragama and Ambakote areas. After these earthquakes occurred, we started investigating them using seismic data to understand their source characteristics. Firstly, we employed template matching technique to detect events that have similar characteristics to the felt events. What we do here is that we use the waveforms and the P and S arrival times of the known events as templates and scan them through the continuously recorded data and try to match the waveforms. We used waveforms at the broadband seismograph in Pallekele for 4 felt events as templates, and use them to scan the continuously recorded data from July to December 2020. With this, we were able to detect 51 events with similarities greater than 0.5, and 17 of these events had similarities greater than 0.7. The figure on the bottom right shows the template event on the 29th August and a detection from the template event on 10th September, and there's a similarity of 0.93 between the template event and the new detection. This is a very remarkable similarity of waveforms, and it suggests that these two events occurred within close proximity to each other. Our location estimates confirm this, and I will talk about this in a few minutes. The plots on the left hand side of this slide are the 3 component waveforms recorded at the seismograph in Palikale for the 5 felt earthquakes, and they all show similar characteristics in waveforms except for their amplitudes, and this suggests that they are mutually close ruptures, faults failing under a uniform stress field. The S to B amplitude ratios are greater than 1, and it indicates that they are natural earthquakes. And the heat map on the right hand shows the spectrogram of the waveforms of the vertical component at the broadband seismograph in Palikale for the earthquake on the 29th of August. Here the brighter colors show strong arrivals, and with this we can clearly identify the P and S wave arrivals, and the fact that there are no strong arrivals after the S wave arrival provides evidence to say that these tremors are not a result of a cavity collapse. So to locate where the earthquakes, to locate the earthquake locations or the hypocenters, we employed 2 techniques. Due to the sparse network of seismographs in Sri Lanka, firstly we employed a single station back projection method. With this we calculate the back azimuth of the source and the emergence angle at the station, and using this back azimuth and the emergence angle and also the S to B time lag, we calculated the hypocenter of the earthquakes. And then we also used the travel time inversion method when the earthquakes were recorded by at least 3 seismographs. In this method, the hypocenter is inverted by minimizing the travel time misfits by ray tracing based on a one-dimensional seismic velocity model. The figure on the left hand shows the locations of 20 earthquakes that we located using the single station method, using the waveforms recorded at the broadband seismograph at Palikale. In this plot, the epicentral locations cluster around Haragama and Anuragama, suggesting that the source of the seismicity is in this region. The depths to the earthquakes range from 0.7 kilometers to 3.7 kilometers, and the figure on the right hand side shows the locations of 3 earthquakes that were estimated using the travel time inversion method, and for this we used the waveforms recorded at Palikale, Mahakanadra and Hakmane broadband seismographs, and also the waveforms recorded by the accelerometers of the monitoring stations at Victoria and Kotmale dam sites. And the earthquake locations from both these methods are very proximal to each other, and their depths are also consistent. The table on this slide provides a comparison of the estimated hypocentral locations from the 2 methods. The order of average epicentral error is plus or minus 2 kilometers. Well, as you can see, the addition of the dam sites for travel time inversion provide a good station coverage and helps us to constrain the hypocenters more accurately. The map on the right hand side shows the error ellipse for the August 29 event, which used the seismic data recorded by the broadband seismographs and also the dam sites. But for the November 18th event, we had waveforms only at Palikale, Mahakanadra and Hakmane broadband seismographs. So for this event, our error ellipses are pretty high. So it clearly indicates that incorporation of data from dam monitoring stations helps us to constrain the earthquake locations more accurately. So then we inspected the first motion polarities of the waveforms recorded at the broadband seismographs and also the accelerometers at the dam monitoring stations. So the polarities of the waveforms in this map are not very clear, but the first motion polarities at these stations are neither all up nor all down, as mentioned in the top right of the two maps. And these first motion polarities provide unequivocal evidence to show that the tremors are not a result of an explosion or an implosion, something like a cavity collapse. The probabilistic focal mechanism inversion for the August 29 event in the figure on the left suggests two fault plane solutions with a probability of 79%. The first one has a strike of 120 degrees, a dip of 18, and a rake of minus 48 degrees, and the second fault plane solution has a strike of 265 degrees, a dip of 77 degrees, and a rake of minus 10 degrees. Then we calculated the radiation patterns for the two fault plane solutions obtained from the probabilistic inversion of first motion polarities. Figures on the left show these patterns for both P and S waves. And the comparison of these radiation patterns with the felt intensity mapped by the GSMB suggests that the fault striking 128 degrees is the likely fault that ruptured. So to summarize, we demonstrated a set of techniques that can be used to analyze seismicity in regions with a sparse network coverage, and we detected 20 microearthquakes that occurred around Haragama, Anuragama and Alutwatte regions during a period of 3 months. And the evidence we provided here point out that these are natural earthquakes likely resulting from the reactivation of existing weak structures. And we advocate the openly sharing of seismic data collected by different organizations in Sri Lanka, and it will be a big step forward in analyzing the seismic risk in the country. And we would like to acknowledge Professor Chandra Jayasena, Engineer S.R.K. Aruppala from the Mahaweli Authority, and Mr. Shanil Kuggalpaya from the Department of Geology for sharing the seismic data from Victoria and Kotmale dam sites.